Inside the bomb-damaged dockyards of Portsmouth in the spring of 1941, Admiralty inspectors conducted a frantic audit of emergency spare parts for British battleship gun turrets. German bombers were pounding the English coastline daily, meaning every spare gear, shaft, and bolt could mark the exact line between naval victory and total catastrophe. Tucked away among salvaged metal in an auxiliary workshop, inspectors uncovered an unlisted, heavy screw-cutting lathe. Its cast iron bed was blackened with oxidized oil, its brass fittings dull, and its maker's mark almost worn away. Out of simple curiosity, a chief inspector attached an optical measuring gauge to test the pitch accuracy of the machine's 6-foot lead screw. This master screw was forged in the late 18th century, decades before standard wire gauges or electrical sensors existed. What the dial gauge showed shocked the entire inspection team. Across 72 full inches of thread travel, cumulative pitch error was less than 1/10,000th of an inch. In 1797, hand-turned screws routinely varied by 1/16th of an inch over a single foot of length. Yet here was an artifact of early blacksmithing that matched the exact manufacturing limits of a mid-20th century airplane factory. How could an 18th century craftsman using coal fires, hand chisels, and simple grease reach microscopic geometric accuracy when everyone else hammered out bolts by eye? This dark metal machine concealed a silent secret. Welcome to Rivet and Rebar, where we explore the industrial giants and machines that built our world. If precision engineering and forgotten industrial history interest you, please take a second to hit the like button and subscribe to our channel. Now, let us travel back to where this unbelievable story first began. To comprehend how this impossible level of accuracy came into existence, we must travel back to the smoke-filled banks of the River Thames in the late 18th century. The Royal Arsenal at Woolwich was noisy, smoky, and hot. Furnaces melted iron ore into liquid fire, while horse teams dragged heavy cannon barrels across wet cobblestones. In 1783, 12-year-old Henry Maudslay walked into this tough workplace to earn his daily bread. He began at the very bottom, packing black powder into artillery shells as a young powder monkey. But young Maudslay was not built for simple routine labor. His eyes were constantly drawn away from powder barrels toward the bright forge fires of the smithy. At age 14, Maudslay persuaded the master smith to transfer him directly into the metal shop. Surrounded by hearths and anvils, his talent for shaping metal quickly showed. Maudslay possessed an intuitive grasp of geometry and metallurgy. While other apprentices struggled with basic iron hoops, he filed hot steel to limits that amazed veteran craftsmen. He did not merely hammer metal, he guided it into absolute obedience. Legend spread fast across Woolwich of the young smith filing 2 cast iron blocks so completely flat that atmospheric pressure alone locked them together when pressed face to face. Word of this teenage prodigy reached London, where inventor Joseph Bramah was facing a massive business nightmare. Bramah had patented a revolutionary safety lock that was virtually unpickable, securing the bank vaults of London's wealthiest merchants. Demand exploded across Europe, but Bramah hit a solid wall in manufacturing. The lock relied on delicate internal sliders and precise key notches. In the 1780s, every part was hand-filed by locksmiths. No 2 locks were identical, parts could not be swapped, and production crawled at an agonizing pace. Desperate for a practical solution, Bramah sent for the 18-year-old metalworker from Woolwich. Step into Bramah's workshop, and you would see Maudslay reshape the entire concept of manufacturing. Within months, he built guide jigs and cutters that allowed basic workers to make identical lock parts. But as Maudslay surveyed the bustling shop floor, he realized Bramah's lock problem was merely one symptom of a much larger disease affecting human civilization. Before Henry Maudslay, the world was built almost entirely on guesswork. If a gear stripped a tooth in 1790, A craftsman spent 3 days making a custom replacement. Nothing was standardized. Screws were cut by hand, holding a chisel against a spinning bar of soft iron on a wooden foot-treadle lathe. If the craftsman's arm twitched, the thread pitch drifted. If his muscles grew tired after hours of turning, the thread depth became uneven. As a result, every single nut was married to one specific bolt. If you mixed up 10 bolts on a workshop floor, none of them would thread into the wrong hole. Consider what that situation meant for a rapidly growing industrial society. Engineers could not build dependable steam engines, textile looms, or naval armaments when every single joint was a custom, non-standardized compromise. Human muscle flexes under heavy load while manual hands tire after long hours of labor. Physical body movement vibrates during cutting. As long as the cutting blade was guided by a human arm, manufacturing remained bound to human frailty. Aware of this fundamental bottleneck, the inventor understood that he had to banish the human arm from the cutting process entirely. He needed to replace soft flesh with rigid, unyielding cast metal. His major breakthrough arrived in 1797 with the slide-dressed screw-cutting lathe. The basic concept sounds deceptively simple to modern eyes, but in the late 18th century, it represented a philosophical revolution in toolmaking. On older lathes, the worker pressed a chisel against a simple rest bar, straining his arms. Maudslay discarded the loose T-rest and mounted the cutting chisel directly into a heavy slide carriage. This carriage clamped the tool bit in an immovable steel vise, moving along hand-scraped dovetail ways that eliminated all human tremor, arm fatigue, and cutter chatter. Behind that innovation came his true stroke of mechanical genius, the master lead screw and change gear train. Maudslay mounted a master steel rod along the frame. Linking the turning spindle to the lead screw with brass gears forced the carriage forward at an exact speed per turn. Engaging a split nut around the lead screw locked the cutting carriage into mathematical synchronicity with the rotating workpiece. Across the entire manufacturing world, the path of a cutting blade was now governed not by human muscle, but by pure mathematical geometry. If you set the gear ratio, the lathe would cut a perfectly uniform screw thread, identical every single time, across any length of steel. Tolerances shrank instantly. They dropped to less than 1/30th the thickness of a sheet of paper. Seasoned cast metal swallowed machine vibration, holding the tool bit with absolute, merciless rigidity. Once outside Bramah's shop following a pay dispute, the machinist established his own independent workshop on Margaret Street in London. They published no secrets or hidden patents. Instead, they offered clear prices and standard machine work to every customer who entered their doors. He created standard thread pitch tables in his own shop, establishing the foundation for all modern fastener standards. His workshop turned into a true temple of mechanical truth. For the first time, a bolt made in London threaded smoothly into a nut made in Manchester. Vertical integration, standardized fasteners, and interchangeable parts were no longer theoretical dreams. They were physical realities etched in solid metal. Global war soon put this revolution to the ultimate practical test. By the turn of the 19th century, Napoleon Bonaparte was consolidating his grip on continental Europe, and Britain's defense rested entirely on the timber and canvas of the Royal Navy. A single 74-gun ship of the line required over 1,400 wooden pulley blocks to manage its rigging lines and hoist its heavy naval cannons. Across the entire British fleet, the Admiralty consumed more than 100,000 rigging blocks every year. Every wooden block was shaped by hand by traditional carpenters. At sea, wooden pulleys split, metal pins seized, and ropes jammed in rough grooves. Dockyards ran low on replacement blocks, threatening to stall Navy ships during danger of invasion. Enter Marc Isambard Brunel, a brilliant French engineer living in England who envisioned a radical solution. An automated, steam-powered factory that could mass-produce wooden pulley blocks with absolute mechanical precision. But Brunel faced a major hurdle. His complex plans required 44 distinct all-metal machine tools, shaping machines, mortising chisels, scoring engines, and corner-rounding lathes that had never existed in human history. To turn his paper blueprints into reality, Brunel turned to Henry Maudslay. From 1802 to 1808, working in his London shop, Maudslay designed and constructed the world's first fully integrated mass-production machine system for the Portsmouth block mills. He constructed 44 specialized metalworking machines, forged from heavy frames and fitted with hardened steel cutters. Every gear, shaft, spindle, and slide rest was machined to standards never before attempted in industrial manufacturing. Powered by steam, the new factory delivered amazing results. 10 basic workers using automated machines made 130,000 blocks a year, beating 110 craftsmen. The blocks were stronger, lighter, and identical down to a fraction of a millimeter. When British warships traded broadsides with French fleets at Trafalgar, their rigging lines ran through pulleys cut by Maudslay's machinery. War tested the machinery, and the machinery held the line. Which brings us directly back to the great mystery of Portsmouth Dockyard in 1941. How did Henry Maudslay, working in 1797 without modern electrical instruments, achieve a lead screw accuracy of 1/10,000th of an inch? How do you create absolute perfection when you have no master standard to copy? To solve this mystery, we must examine one of the most profound intellectual breakthroughs in industrial history. Maudslay's invention of the three-surface method. Maudslay recognized a fundamental paradox of metrology. If you rub two metal plates together with abrasive paste, they will appear to fit perfectly. However, they are not necessarily flat. One plate could be slightly convex while the other is equally concave, mating together like a ball and socket while hiding their geometric errors. Armed with pure logic, Maudslay took 3 separate cast iron plates, labeled A, B, and C. He hand-scraped plate A against plate B until their surfaces matched. Next, he scraped plate B against plate C. If there was any curvature present, plate A and plate C would fail to mate when brought together. By scraping plate A against B, B against C, and C against A in turn, he removed all shape errors. The only geometric state where all 3 plates touch across their entire surface simultaneously is absolute, uncompromising flat plane perfection. Over raw metal and crude tools, realize what Maudslay accomplished. He generated absolute physical truth out of raw iron using human logic and a simple hand scraper. Lathe bed alignment relied on those flat reference surface plates as a master standard. Next, he tackled the lead screw. He forged a solid brass rod and spent months hand-chiseling a preliminary spiral thread. Using a crescent steel knife riding in a guided rig, he turned the screw thousands of times, filing away microscopic high spots under magnifying lenses until thread pitch across the bar was mathematically uniform. Verification came in 1805 when Maudslay built a bench micrometer named the Lord Chancellor. Built with brass frames and a fine lead screw, its dial measured sizes down to 1/10,000th of an inch. It was so sensitive that if Maudslay held his warm hand near a steel bar in its anvils, the pointer would spin, tracking microscopic thermal expansion caused by body heat. That lead screw inside the 1941 Portsmouth lathe was generated directly from Maudslay's master screw lineage. It was the physical manifestation of an unyielding geometric system created out of nothing. During the next half-century, Maudslay, Sons and Field reigned as the undisputed titan of heavy engineering. From their sprawling Lambeth works on the Thames, the company built the largest marine steam engines on Earth. They forged the giant propulsion machinery for HMS Rattler, the Royal Navy's first screw-propelled warship, and powered Isambard Kingdom Brunel's magnificent transatlantic steamship, the SS Great Western. The firm was a cathedral of heavy manufacturing, where massive steam hammers shook the London subsoil and giant vertical boring mills machined steam engine cylinders 12 feet in diameter. Yet no corporate empire is immune to the slow rot of time. Following Maudslay's death in 1831, the company passed into the hands of his sons and subsequent business partners. For decades, the sheer momentum of Maudslay's reputation carried the firm forward. But as the late 19th century arrived, the winds of global industry shifted. Shipbuilding moved north to the Clyde and Tyne rivers, where cheap coal and raw steel lowered production costs. Meanwhile, speculative managers took control of London's engineering boards, diverting vital capital away from factory upgrades toward short-term speculative payouts. Leadership prioritized dividends. They ignored electric motor drives and high-speed tool steels. By the late 1890s, mounting losses against leaner northern competitors eroded market share until private liquidators stepped in during 1900. The company collapsed. The famous Maudslay, Sons and Field was forced into receivership. The massive Lambeth works, which had forged the muscular foundations of the British Empire, was closed down. Its machine beds were unbolted. Its historic tools sold off at public auctions for scrap value, and its brick foundries demolished to make way for urban real estate development. The corporate entity that dominated 19th century manufacturing evaporated into paper ledgers and bankrupt estate filings. A company can be liquidated and its factory bulldozed into dust, but geometric truth endures. Though the empire of Maudslay, Sons and Field collapsed under Victorian corporate miscalculations, Henry Maudslay's true legacy propagated across the globe as a mechanical genome. Within his Lambeth workshop, every titan of the Industrial Revolution learned their craft. Joseph Whitworth worked at Maudslay's bench, absorbing the three-surface method to create the world's first standardized screw thread system. Richard Roberts invented the iron planer. James Nasmyth invented the steam hammer. Joseph Clement developed heavy slide lathes that powered early mechanical computing engines. Look around a modern machine shop today. Whether it is a multi-axis CNC milling center, an ultra-precise cylindrical grinder, or an aerospace measuring machine, every single one relies on the geometry established by a London blacksmith in 1797. The hand-scraped dovetail ways, precision lead screws, and rigid cast beds are not merely historic inventions. They are the immutable laws of metalworking. You can liquidate a corporation and bulldoze a factory into dust, but you cannot destroy geometric truth. In machine shops around the world, solid lathe beds made long ago are fitted with digital readouts, turning steel to fine limits. Heavy metal swallows vibration, carrying a generosity of quality that short-term private equity will never understand. Master Henry Maudslay built his enduring legacy in solid iron, and solid iron stands the test of time. Thanks for watching Rivet and Rebar. If forgotten industrial sagas and precision engineering are your thing, take a moment to like and subscribe. Click the video on your screen right now to explore how a patent war over steam hammers nearly destroyed America's rail lines. Keep the iron burning.